So as you have probably guessed, positive integers are represented in the computer simply expressed as their binary equivalents. So say 13 decimal is stored as the bits 1011, and that's simply the binary equivalent of 13 decimal. Representing negative integers, though, is a problem, because you can't just put a negative sign in front of the bits. That doesn't make any sense, because all we have are bits to express any data. So the first thing we need to do is we need to establish how many bits we're using to represent the integer, and then we can say the most significant bit, that is the leftmost digit when you write the number out. We use that to indicate the sign, so 0 meaning positive, 1 meaning negative. However, there's more to it because the negatives are written in 2's complement form, wherein the highest bit is still effectively indicating the sign, but the numbers loop around from the highest positive number to the lowest negative number, and this will require some illustration. For now, just understand that, say, if I have this positive number, which is decimal 107, I can't make it negative 107 simply by changing, this is not, in 2's complement form, this is not negative 107. So there's a bit more to it. So first let's just look at what if you were to use 4 bits to represent an unsigned integer. That is, we're using these 4 bits to always represent a positive quantity, never a negative quantity. Effectively, we have a 4-bit counter. So I've written it out here in a loop, because it's good to think of it in a loop, because we start at 0, and then we count, add 1, go to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then when you get to 1, 1, 1, and you add 1, you essentially are cycling back down to 0, 0, 0. Because remember, we're restricting ourselves to 4 bits. So you can think of it like the 1 got pushed off the end here. And the important point is that we go full circle. Now imagine that we're going to use 4 bits to represent a signed integer, that is, integers that are both positive and negative. Well, it's really the same idea. You start with your counter at 0, and it looks exactly the same all the way up to positive 7, but now when we get to 1 and then 0, 0, 0, 0, what this actually represents is we get into negative territory. And in fact we start with the negative quantity with the highest absolute value, which with 4 bits is negative 8, and then from there we go to negative 7, negative 6, negative 5, and so on to negative 1, which is 1, 1, 1, 1, and then from there we go back to 0. Now I'm sure you're wondering why we use this 2's complement scheme when it seems much more straightforward and more intuitive to simply just use the most significant bit to indicate the sign, such as say positive 5, 0, 1, 0, 1 would be represented with simply as negative with simply the bit set to 1, the highest bit set to 1. The most important reason for using 2's complement is that it makes arithmetic more efficient for processors to do. More trivially, it also noticed that the difference is that in 2's complement we only had 1 0, whereas in this scheme we have both positive 0 and negative 0, which is a bit odd. Not really an issue, perhaps, but it's an important difference to note. Also notice that in this scheme, the absolute value of the biggest positive number and the smallest negative number are the same, whereas in the 2's complement scheme, we had positive 7 and negative 8. So in the 2's complement scheme, because we only have 1 bit pattern to represent 0, we can then use that remaining bit pattern to represent negative 8. One more negative number, which is really, again, not a big deal, and not really the purpose behind the 2's complement scheme, but it is kind of a peculiarity to note. In the 2's complement scheme, there's a simple way of converting between negative and positive, and we call this getting the 2's complement of a number. So say you have this bit pattern, which was an 8-bit integer, which in the 2's complement scheme represents plus 107. And what we do is we first flip the bits, and then we add 1. So say 1, 0, 0, 1, 0, 1, 0, 0. There we flipped all the bits, and then we simply add 1. And this will be negative 107. Or say if we had this bit pattern, which represents negative 35, and we want to see the bit pattern which represents positive 35, we would do the same thing. So it works both ways. 0, 0, 1, 0, 0, 0, 1, 0, and then we add 1, and that is positive 35. So the nice thing is it's going from negative to positive requires the same conversion. It's the same operation. Computers are, of course, physical machines. They're not abstractions. So, of course, they're always dealing with a finite number of bits, never an infinite number of bits. That would be impossible. And so then it's a good idea to know, well, if I had n number of bits, what integers can I represent using just that number of bits? And to answer this question, you need to know, well, how many unique bit patterns can I represent with n bits? And the answer is that 2 to the n. This is because, say you start with 1 bit, and that can represent 2 different bit patterns, 0 and 1, but then if you add 1 more bit, then you're doubling the number of bit patterns representable, 0, 0, 0, 1, 1, 0, 1, 1. And then if you add another bit, then you're again doubling the number of bit patterns, the number of combinations that you can set the bits in. And so for every bit you add, you're doubling it. So that's why it's 2 to the n. So, for example, because 2 to the 5th is 32, 5 bits gets you 32 bit patterns, and then 2 to the 8th is 256, so 8 bits gets you 256 bit patterns, and 2 to the 16th is 65,536, and so on. What this means for unsigned integers is that the range of integers is 0 to 2 to the nth minus 1. The reason is because we are using one of those bit patterns to represent 0, therefore rather than having, say, 256 if you use 8 bits, the highest value representable is 255. For signed integers, remember, we're using half of the bit patterns to represent negative numbers, therefore the formula is a bit different. It's 0 to 2 to the n minus 1, and negative 1 to negative 2 to the n minus 1. It looks a bit confusing, but it's actually quite simple. So 8 bits used to represent signed integers has the range 0 to positive 127, and it also has the range negative 1 to negative 128. Because 2 to the 7th minus 1 is positive 127, and 2 to the 7th, negative 2 to the 7th is negative 128.